Hello and welcome to part 5 of these talks about op-amps, in which we'll be looking at the second common form of amplifier, the inverting amplifier. So named because the output inverts the input. In other words, if the input goes up, the output goes down, if the input goes down, the output goes up, and so on. Let's have a look at the circuit and see how it works. Okay, this is a inverting amplifier. You'll see I've connected the non-inverting input just to ground, through a 1K resistor in this case, but for ideal op-amps, the 1K resistor doesn't need to be there. Remember that no current flows into the inputs of an ideal op-amp, so there is no voltage drop across this 1K resistor. The non-inverting input there would just be at 0 volts. So I could redraw this circuit something like this. Non-inverting input connected to 0. Inverting input connected to both a feedback resistor coming back from the output and to an input resistor connected to our input voltage there. And in this case, both of these resistors, the input resistor and the feedback resistor, are 1K. Okay, the easiest way to analyze this circuit is to think about the currents that are flowing. I've got a negative feedback system here, which means that the op-amp is going to be trying to keep its two inputs as close together as possible. And if I can assume that the gain of the op-amp is effectively infinite, then I can assume that the two inputs, the non-inverting input and the inverting input, are at the same voltage. In other words, the inverting input is at 0. Therefore, the current flowing through this 1K resistor from V in, I'll call it I in, is just going to be equal to V in minus 0, because this point here is at 0 volts. It's sometimes called a virtual ground or virtual earth because it's kept at 0 volts, although it's not actually connected to ground. V in minus 0 divided by this resistor here, which at the moment is 1K. In general, I could call that R in. None of that current flows into the op-amp, because one of the properties of an ideal op-amp is that no current flows into its inputs. Therefore, all of that current must flow through this resistor here. In general, I could call that RF, the feedback resistor. And therefore, the voltage across the feedback resistor must be the current flowing through it times the value of the feedback resistor. And since the current is flowing through it from this direction to this point, from the inverting input to the output, that would give me that the voltage on the inverting input minus the voltage at the output is equal to the current flowing, which is this, times the value of the resistance, RF in general. It's just Ohm's law again. The voltage across this feedback resistor is the current through this feedback resistor times the value of the feedback resistor. Well, we know that V minus, the inverting input voltage, is being kept at 0 volts by the action of the op-amp, and therefore I can just write V out equals minus RF over R in times V in. That minus sign is why it's called an inverting amplifier. When the input goes up, the output will go down, and vice versa. You might notice that unlike the non-inverting amplifier, it's possible to get a magnitude of this gain which is less than 1. All you need to do is have an R in, the resistor here, bigger than RF. For the non-inverting amplifier that we looked at last time, the result that we got was this. and it's impossible to have an output which is smaller than its input. The magnitude of this gain here is always bigger than 1. We can see that this equilibrium result is stable because if the output here ever went slightly below its equilibrium value, then that would cause more current to flow through this feedback resistor, which would reduce the voltage at this point here, and that would reduce the voltage at the inverting input, but that would act to increase the output voltage to compensate. Similarly, if the output voltage ever went too high, that would reduce the current flowing through this potential divider here. That would increase the value of the voltage here. That would decrease the value of V plus minus V minus for this op-amp, and that would tend to pull the output back down again. So this is a stable equilibrium point. We can see this circuit working in the simulator as well. Here I haven't bothered to put in this extra 1K resistor between the non-inverting input and ground. And you can see that a 1 volt input is just producing a minus 1 volt output. If I made this feedback resistor 2K, then I would have a minus 2 volt output from my 1 volt input. If I made it 3K, the gain is minus 3. So 1 volt would give me a minus 3 volt output, or a minus 1 volt input would give me a plus 3 volt output, and so on. One important point to note about this circuit is that, unlike the non-inverting amplifier, if you remember, the non-inverting amplifier looked like this. An inverting amplifier requires some current to flow out of its source. So it is loading its source in the sense that it requires current to flow. The non-inverting amplifier doesn't. For an ideal op-amp, there is no current flowing into the inputs of the op-amp, so no current is required to flow out of our voltage source, whatever is providing V in. For the inverting amplifier, that's not true, and current is having to flow out of our voltage source here. In the case where our voltage source has a Thevenin resistance, which is of a significant value, that's an important point to keep in mind. Okay, that's the two fundamental forms of amplifier described. Next time, we're going to see an important variation on the inverting amplifier, the summing amplifier.